Up next, we're going to do some examples involving equations of planes. Now, the goal for the equation of a plane is to find a normal vector as well as a point contained within the plane. So, first example, nice little softball example, get us warmed up. Find the equation of the plane that is orthogonal to the given line with symmetric equations. X minus 2 over 2 is equal to y plus 3 over negative 1, which is equal to z minus 7 over 4, and passes through the point 2, negative 4, 1. Now, given that it's orthogonal to this given line, that means that the normal vector for our plane is going to be the same as the direction vector for the given line. So normal vector for the plane is going to be equal to the directional vector of the given line. Now the idea is that direction vector is going to be whatever we see in these denominators. Those would have been our coefficients of t if this was in parametric form. So 2, negative 1, 4. The point that we have contained within this plane is the point 2, negative 4, 1. That was also given to us. After that, it's simply a matter of tossing all of this into the standard form for a plane. Standard form for a plane says take the component of the vector and multiply by the variable minus the starting point. All of that's going to be equal to 0. So for x, we'll see an x minus 2. For y, we'll see y plus 4. And for z, we'll see z minus 1. Now, on the off chance that you're interested in converting this over to general form, we can distribute this 2, distribute the negative 1, and distribute the 4, and combine all the like terms that we see. So this will be considered standard form. So negative 2x minus 4, minus y minus 4, plus 4z minus 4. Wow, lots of minus 4's in here. Not on purpose, but I'll take it. So the general form for this plane would be 2x minus y plus 4z minus 12 is equal to 0. Another acceptable form would be if you were to move that minus 12 over to the right-hand side, that would work as well. That was supposed to be a check mark. I don't know if that translated appropriately. Check mark. There we go. All right, nice little warm-up problem. Let's try another. So this time, I'm going to give you 3 points. 3 points will uniquely define a plane, assuming that they are not all collinear. What we're going to do is find the equation of the plane passing through these 3 points. 1, 0, 1, 2, 2, 3, and negative 1, 4, 7. Now, in order to find the plane containing 3 given points, what we're going to do is take those 3 points, turn them into 2 vectors with the same initial point. Wow, I completely missed, and there, now I didn't miss. We'll turn it into 2 vectors within the plane, then taking their cross product will give us our normal vector that we're looking for. So first off, just to label these things, we'll call these points P, Q, and R. And I'm going to be interested in finding the vectors PQ as well as PR. So vector PQ, which is a vector within our plane, will take terminal minus initial. So 2 minus 1, 2 minus 0, and 3 minus 1, giving us the vector 1, 2, 2. Good stuff so far. Now, you could go with PR, you could go with QR. Basically, as long as you're using the point R as another point in here, that is the important thing. So we'll see negative 1 minus 1, 4 minus 0, and 7 minus 1. So it'll be negative 2, positive 4, and positive 6. A quick check lets me know that these vectors are not parallel to each other because they are not multiples of one another. To get our normal vector, we'll take the cross product of these two. The order in which you take the cross product does not matter. You can do PQ cross PR or PR cross PQ. So we'll put the components of the first vector, 1, 2, 2, across the middle row, and we'll put negative 2, 4, 6 across the third row. Recopy the first 2 columns. Just going to give you a little slashy. Hope you don't mind. Any slash coming out of the bottom we account for with a plus sign. 2 times 6 for the I component. 2 times negative 2 for the j component. and 1 times 4 for the k component. Then, go and give it a little slashy the other way. Negative 2 times k, that'll be negative 4k. 2 times 4 times I, that'll give us plus 8i. And then 6 times 1 times j, that'll be 6j. Combining all of the like terms that we see, we'll start with i's. I have 12 minus 8, that'll be 4. For j, I see negative 4 minus 6, that'll be negative 10. And then 4 minus negative 4, I believe, is going to give us 8. This, again, is the normal vector for our plane. 4, negative 10, 8. If you want to do a quick check just to make sure that you're on the right track, try dotting this vector with the other two vectors PQ and PR. If you get 0 in both cases, then what you have is definitely a normal vector. As far as a point within the plane is concerned, you are welcome to use any one of these 3 points. I'm going to stick with P because I'm a simple man. So the equation of our plane is going to be 4 times x minus the corresponding coordinate, x minus 1, minus 10 times y minus its corresponding coordinate, that's y minus 0, plus 8 times z minus the corresponding z coordinate, and that'll be 1. All of this is going to be equal to 0. This would be considered standard form. If you're interested in leaving it in this standard form, that's totally fine. Otherwise, if you want to distribute the 4, distribute the 10, and distribute the 8, and then combine a bunch of like terms, that's fine as well. So let's see what we get when we do that. No distributive property for the second part, which is fine. Combining the negative 4 with the negative 8, we'll call this 4x minus 10y plus 8z minus 12 is equal to 0. Additionally, if you feel like dividing both sides by 2, since it's a greatest common factor throughout, you're of course welcome to do that. Now the ultimate check is going to be take all 3 of the original points that we had and try plugging them in to the given equation that we had at the end. If they all satisfy the equation, then you have the unique plane that you are looking for.